Welcome to today's Explainer. We are diving right into the fascinating foundational building blocks of mathematical sequences. We're going to break down these complex, abstract concepts into perfectly organized, bite-sized pieces, and we'll see exactly how infinity can be tamed. Okay, let's lay out our roadmap for today. 1. Meet the sequence. 2. Convergence and divergence. 3. The limit toolkit. 4. Monotonicity and boundedness. And finally, 5. Recursive sequences.
All right, part 1, meet the sequence.
So, at its core, a sequence is really just an ordered list of numbers. Formally speaking, it's a function that maps natural numbers, 1, 2, 3, and so on, to real numbers. We usually represent this as a sub n, where n is just the position in our ordered list. Now, there are two classic patterns you're going to encounter constantly, and they brilliantly illustrate the fundamental difference in how mathematical structures grow. First, we have the arithmetic progression, which builds by simple addition. You just keep adding a constant difference d to get to the next term. Then, contrast that with the geometric progression. This one scales by multiplication, relying on a constant ratio r to jump from one term to the next. Simple addition versus scaling multiplication, it's a really beautiful contrast.
Moving right along to section 2, convergence and divergence.
So now that we understand how a sequence actually grows, we have to ask the ultimate question. What happens as this thing marches off toward infinity? Let's start with convergence. Intuitively, a sequence converges if its terms get arbitrarily close to a specific, finite destination. We call that destination the limit, or L. But mathematicians, of course, love their precision, which brings us to the rigorous epsilon n definition. It basically says that for any tiny margin of error you choose, that's your epsilon, there is a specific point in the sequence, n, after which all the subsequent terms stay strictly within that tiny margin around our limit L.
But on the flip side, we have divergence. A sequence diverges if that neat single limit simply doesn't exist. And this can happen in a few different ways. The sequence might just shoot off endlessly into positive or negative infinity, or it could wildly bounce back and forth forever, kind of like the classic example of -1 to the power of n. That one just endlessly oscillates between -1 and +1 without ever actually settling down.
Which brings us to section 3, the limit toolkit.
This is where we get to equip ourselves with the practical tools and theorems we need to actually tame infinity and calculate these limits with total confidence. First out of the toolkit is the geometric sequence theorem. Remember that constant ratio r we talked about? Well, it completely dictates the ultimate fate of a geometric sequence. If r is strictly between -1 and 1, the sequence shrinks down and converges perfectly to 0. If r is exactly 1, it just stays at 1. But if r is strictly greater than 1, it explodes to infinity. And if it's less than or equal to -1, it oscillates and diverges. Literally, one simple ratio tells you the entire story.
Next up, we have the sequence limit laws. I actually love these because they prove that limits behave totally predictably. If you know the limits of two separate sequences, you can combine them just like you would in regular algebra. You can add them together, multiply them by a constant, multiply them by each other, or even divide them, as long as that denominator's limit isn't 0, of course. And the power rule works the exact same way. It really makes evaluating complex sequences incredibly efficient.
But hey, what happens when the algebra isn't so clean? How in the world do we handle a mathematical mini-mystery like the cosine squared of n, all divided by 2 to the power of n? That numerator is wildly waving up and down, making it look almost impossible to pin down a clean limit.
Well, enter one of my absolute favorite mathematical concepts, the Squeeze Theorem. I kind of like to think of this as mathematical peer pressure. If you have a wild, unpredictable sequence, let's call it b sub n, but you can definitively prove it is forever trapped between a lower sequence a and an upper sequence c, you're in control. If both of those outer sequences are heading to the exact same limit, let's say 0, then they physically squeeze that wild middle sequence, forcing it to go to 0 as well. It is just an incredibly clever workaround.
Another amazing tool is for when sequences are trapped inside continuous functions. We have this step-by-step procedural recipe that completely demystifies those terrifying-looking equations. Let's try it with an example, using tangent. Instead of panicking, you just work from the inside out. Step 1, isolate and compute the limit of that inside sequence. In our case, the limit of 2n minus pi over 1 plus 8n simplifies really nicely to pi over 4. Then step 2, you just apply the outer continuous tangent function to that result. Tangent of pi over 4 equals 1. Boom, problem solved, just like that.
All right, on to section 4, monotonicity and boundedness.
We are now digging into some advanced behavioral traits of sequences, specifically looking at their directional commitment and spatial limitations. First up is monotonicity. Basically, a monotonic sequence is one that picks a direction and absolutely refuses to second-guess its path. It is either strictly increasing, meaning every single new term is larger than the last, or it is strictly decreasing, meaning every new term is smaller. There is simply no backtracking allowed.
So how do we actually prove, rigorously, that a sequence is locked into a single direction? Well, we have 3 highly actionable testing methods. 1. The derivative test. You just treat it like a function. If the derivative is positive, it's increasing. 2. The difference test. Subtract the current term from the next term. If that result is greater than 0, it's going up. And 3. The ratio test. Divide the next term by the current term. If the result is greater than 1, it's increasing. Having these 3 options is great because you can always just pick the one that makes your specific equation the easiest to solve.
Next up, spatial limitations, boundedness. You can think of this like an invisible mathematical ceiling and floor. If a sequence has an upper bound, m, it never breaks through that ceiling. If it has a lower bound, m, it never drops below that floor. And if it has both, we say the sequence is fully bounded, meaning it's completely trapped within that specific vertical space.
Okay, pay super close attention here, because this is a classic trap that catches students all the time. It is absolutely true that every single convergent sequence is bounded. It has a destination, right? So it stays contained. However, a bounded sequence is not necessarily convergent. Remember our oscillating friend, -1 to the power of n? It is perfectly bounded by -1 and +1, but it just bounces forever without converging. So boundedness alone just isn't enough.
So the crucial point we are driving at is this magnificent combination right here, the monotone convergence theorem. This is literally the golden rule of real analysis. If you can prove a sequence is bounded, meaning it's trapped below a ceiling, and you can prove it is monotone, meaning it is always strictly increasing and pushing upward, then it has absolutely no choice but to converge. It can't go down and it can't break the ceiling, so it must settle at a limit. It's a wonderfully logical, undeniable conclusion.
And finally, Section 5, recursive sequences.
Up until now, we've mostly looked at sequences where you can just plug in any number n and boom, you immediately get the answer. Recursive sequences are a whole different beast. In a recursive sequence, every successive term relies completely on the one that came just before it. The next term, a sub n plus 1, is actually a function of the current term, a sub n. It acts like this endless self-feeding loop. And to get it started, you just need a single starting seed, an initial term defined as a sub 1, and then that relation generates the entire infinite sequence from there. When you encounter a recursive sequence on an exam, you need a solid game plan. Here's a highly practical first step, the monotonicity check. Because recursive sequences feed on themselves, establishing whether they are consistently increasing or decreasing should always be your very first move. You do this by calculating the difference between the next term and the current term. Once you lock down its direction, you can look for its bounds, and then apply that monotone convergence theorem we just learned to effortlessly find its limit. And just like that, we have decoded the foundational principles of real number sequences. You've seen exactly how geometric ratios dictate fate, how the Squeeze Theorem leverages mathematical peer pressure, and how bounds combined with direction guarantee convergence. So, now that you possess the mathematical blueprints to practically tame infinity, the real question is, what mathematical structures will you build next? Thank you so much for exploring these concepts with me today. Keep that curiosity alive, and I'll catch you in the next explainer.